This video is a guide to calculating the elastic potential store of an object. That is the energy store associated with stretching, squashing, or twisting an object. So we'll start by looking at the equation. We have EEP, which is energy elastic potential, is equal to a half KE squared, where K is the spring constant, which is how difficult it is to stretch, squash, or twist a material, and E is the extension, that is how far the material has been stretched, squashed, or twisted. So for a spring constant that's large, that means the spring is stiff. It means it is difficult to make it stretch, squash, or twist. So remember that energy is measured in joules, spring constant is measured in newtons per meter, and the extension is measured in meters. So let's look at some calculations. A bow with a spring constant of 400 newtons per meter is stretched 0.5 meters with a force of 200 newtons. Calculate the elastic potential store of the bow. So we start by writing our equation. Now we need to pick the correct numbers to go in the correct places here. We have K the spring constant and E the extension, but we have three different numbers to choose from. So first of all, we can easily identify K because it says in the question spring constant of 400 newtons per meter. So we replace the K with a 400. It is stretched 0.5 meters with a force of 200 newtons. Now we know that extension is measured in meters, so we must be picking the 0.5 meters. So E is replaced by 0.5. This gives us a half times 400 times 0.5 squared. We'll start by squaring the 0.5 to give us a half times 400 times 0.25. Once we've multiplied those numbers together, we have that the energy in the elastic potential store is 50 joules. Next, a bungee cord with a spring constant of 45 newtons per meter stretches by 30 meters. Calculate the elastic potential store of the cord. In this case, again, we write down our equation first. The numbers are more easy to identify here. We have 45 newtons per meter, so K is replaced by 45, and we have 30 meters, so E is replaced by 30. This gives us a half times 45 times 30 squared. We'll square the 30 first to give us a half times 45 times 900, and that leaves us with an energy in the elastic potential store of 20,250. Now it's important to note here that we were only given two significant figures in each of the numbers in the question. We had 4 and 5, and we had 3 and 0. So our answer should also be to two significant figures. Once we've done that, by rounding it, we can also simplify this answer. Since it's 20,000 joules, we can call it 20 kilojoules. And finally, a slinky spring of length 0.1 meters and spring constant 0.80 newtons per meter is stretched to a length of 9.1 meters. Calculate the elastic potential store of the slinky. Now in this case we haven't been given the extension. So what we have to do is we have to calculate the extension. The extension is how far that spring has been stretched. So that is the new length, which is 9.1 meters, subtract the original length, which was 0.1 meters. That gives us an extension of 9.0 meters. Once we have the extension, we can look back to the question and see that we already have the spring constant, and so we have EEP equals a half KE squared, replace the K with 0.80 and replace the E with 9.0. This gives us an answer of 32.4 joules. Finally, again, because we've got two significant figures in the question, we can round our answer to approximately 32 joules.